So good afternoon, everyone, and I'm Haider from AMU Aligarh. I'm going to talk about explosive transitions in coupled Lorenz oscillators. This is the outline of my talk. I'll start with a brief introduction and motivation of the problem. Then I'll talk about coupled Lorenz oscillators under symmetry preserving and symmetry broken couplings. Finally, I'll discuss the results and summarize. So the idea of synchronization of chaotic systems was first introduced by Pecora and Carroll. And then since then there had been a lot of different scenarios that have been extensively studied for a wide range of chaotic systems, periodic systems under various coupling strategies. But today's discussion is about explosive synchronization, which is characterized which is an abrupt transition from an incoherent state to a coherent state. And the network, the oscillators that we choose on the network, they have frequency, their frequency is correlated with the degree of the node. And another important aspect of explosive synchronization is that it's a discontinuous transition and it is accompanied by a hysteresis when the coupling parameter is varied in the forward and in the backward direction. So far, the studies on explosive synchronization have focused on phase oscillators or in periodic oscillators. Very few studies are there on chaotic oscillators. So, an example of the Kuramoto oscillators on a star network. So we have these phi dots and psi dots, as these are the phase oscillators on the nodes, and 1 by beta psi dot. So beta over here denotes the frequency correlation, is there to introduce frequency correlation, and the order parameter R is defined in this particular way, such that the star network so this star network, there's a hub. So over hub, the dynamics is given by this equation, and for each node, the dynamics is given by the equation there. And then we plot this order parameter R to show that as we change the coupling strength lambda, we observe that in the forward direction, the transition point is different as compared when we move in the backward direction. Another aspect associated to this idea of explosive transition is that of explosive death, where in which the oscillators, the system makes a transition from oscillatory dynamics to death with increasing in the coupling strength, and vice versa when the coupling strength is decreased. And this is called as explosive death. Again, this transition is accompanied by a hysteresis, and this is a discontinuous transition. And to study this behavior, we introduce an order parameter A, which is based on the difference of the average of the xi variables, the maximas and minimas of the xi variables. And finally, the average, or say the normalized average amplitude, is given by this equation. So here is the system under consideration. We consider a Lorenz oscillator. On the nodes, we are considering these equations, the Lorenz equations, and on the hub, we are considering these equations. So we see that we have introduced this alpha n and alpha h. These are the parameters that have been introduced to control or to change the time scales, to introduce the time scale variation in the system. And the other parameter values that we are considering are such that the system shows chaotic dynamics. And alpha n and alpha h are the time scale parameters. One of the important aspect about Lorenz is that under these transformations, the system remains invariant, which means that if we couple the system in z variable, meaning epsilon z is the coupling strength for z variable, and if we set the coupling strength in x and y is equal to 0, the symmetry is preserved. Whereas it is broken if either of these coupling, either of them or both of them are not equal to 0 and epsilon z is equal to 0, the symmetry is broken. And the order parameter that we define for the Lorenz over here is based again on the phase. I mean, so we redefine this since Lorenz has got multiple centers of rotation, so we introduce a variable u such that it reduces to a single rotation center, and hence we can define the phase phi based on which the order parameter is given by this equation. So in the symmetry preserving case, we observe that the order parameter R makes a jump, but this is not an abrupt jump. There are intermediate points in between, and then finally it goes to the synchronized state. So this is the region where the system is synchronized. And then when we move in the backward direction, the transition is taking place at a different place, at a different value of coupling strength, and hence we see that in moving in the forward and in the backward direction, the transition points are different. And the reason is that because of the occurrence of these attractors that are intermittent attractors. So in Lorenz, there is an attractor A minus, which is associated to the which is produced because of the destabilization of one of the fixed point, and hence we have an A plus there or an A0 there. But in such a complex setting, we have, when we change the coupling strength, it gives birth to two more attractors that are AI plus and AI minus. And the underlying dynamics is that these AI plus and AI minus attractors are intermittently synchronized and desynchronized, and hence we are getting these intermediate points in the transition curve for R. This is the space-time plots and the phase-time plots for the dynamics. So it is essentially calculated for 500 oscillators, but over here I am showing it for 100 oscillators to show the intermittent dynamics, that in between there are lines and then they are suddenly they get disappear. This simply shows that the attractors, the associated attractors are the intermittent attractors. And here is the time series for all the oscillators. So the bigger time series, the time series having very large amplitudes are A0 type, whereas the time series with very small amplitudes are the A plus or A minus type attractors. And here is the parameter space. So we are fixing this parameter values, and we are just plotting the parameter space here. So ds is the desynchronized state, and when we are moving along, say for example, if we are moving along this line, this black line as shown over here, we observe that at this point the system makes a transition, at this point there is a transition to synchronized state, meaning the yellow region. So there is a transition to synchrony, and then it moves in the backward direction. So at this point the system goes back to the desynchronized state if the coupling strength, if the coupling parameter is moved in the backward direction. And then here HA1 corresponds to the hysteresis area corresponding to the transitions between the desynchronized and synchronized state. Similarly, to study the transition from the oscillatory state to death, we plot, for example, along this line, we plot this order parameter A epsilon versus epsilon. We see that there is a proper transition between in the forward and in the backward direction, with the hysteresis area denoted by HA2 over here. And these are the time series for different coupling values. At epsilon z is equal to 0.3 and 0.4. We have, so 0.4, the system goes to the steady state. All of them are going to the fixed point. All the oscillators are going to the fixed point. Here is the parameter space, the alpha h, alpha n parameter space, and we observe that as we increase alpha n, the hysteresis area HA1 increases. And similarly, in the parameter space for alpha n and epsilon z, again we see that with increasing alpha n, we observe that the hysteresis area would decrease for a fixed value of alpha h. Alpha h is the time scale parameter for the hub. And here we calculate the stability of various states. So here we are plotting the the master stability function calculated for different attractors. So, as suggested in this reference, that when there is a multi-stable system, the master stability function should be calculated for individual attractors. So here we have 3 attractors, A plus, A minus, and A0. So the 3 curves over here show the 3 master stability functions. So the transition point over here, this shows that these synchronized states are stable for individual attractors. Here I plot the largest Lyapunov exponent of the system, where we can understand about the dynamics, that it becomes periodic at this point, and then finally the system goes to death when the Lyapunov exponent becomes negative. Then we do the stability analysis, and we calculate the real part of the eigenvalue, and we observe that death takes place in this region, and this is predicted by doing the usual stability analysis. And hence, and finally, here is the transversal Lyapunov exponent calculated for 2 coupled oscillators, and this suggests that this is the point where the system will begin to go into synchronized region. And here is a symmetry breaking case where we observe that for where we choose a specific coupling, that we are fixing epsilon x, coupling in x is 0 and z is 0, but the system is coupled in y variables, and as we vary y, epsilon y, we observe that the order parameter a epsilon shows a discontinuous transition. So here this region, when the order parameter a epsilon is not equal to 0, this is the region where the system has got oscillatory dynamics, whereas in this region the system is in steady state. So we see that it goes all the way along this direction, goes to death, but if it is moving in the backward direction, it goes to oscillatory state for a different value of epsilon y. So, okay. Here is the parameter space and the largest Lyapunov exponents, and we are able to predict the eigenvalues. Through the eigenvalues, we are able to predict the precise point where the system will go to death. Finally, to summarize, we have studied coupled Lorenz oscillators on a star network configuration. In symmetry preserving case, the transition from desynchronous state to synchrony is irreversible in nature, and there is an associated hysteresis. As the strength is further increased, the system makes a transition to death, and this transition is explosive in nature. And in symmetry breaking case, there is always explosive death. The system always shows explosive death. And time, we have observed that the time variation parameters alpha 1 and alpha 2 plays an important role in inducing explosive transition in the system. Okay, so thank you very much.
Thank you for an interesting talk. I want to know about the hysteresis. I mean, is the hysteresis due to the fact that the hub has different parameters, or is it due to the fact that the system has symmetries that coincide, so that coexisting symmetries, and that gives, for instance, rise to different Lyapunov exponents? You can find this behavior already in some papers of us from more than 20 years ago. Thank you. But in other, not in Lorenz, we did it with Rosslers. Something similar. I mean, it's not exactly the same, but the symmetries you can find there.
Okay. Yeah, so symmetries, so the hysteresis that we observe over here is, I think, due to the initial conditions.
To the initial conditions?
Meaning, when we are moving in the backward direction, we are starting with, in the synchronized state.
Yeah.
So the system is already synchronized. Mm-hmm. So the initial conditions we are choosing, these are the initial conditions close to the synchronized state. And we have chosen the cases, we have studied the cases for symmetry preserving cases as well as symmetry broken cases. In each case, there is an associated
But you,
hysteresis.
excuse me, but you are analyzing the whole system in forward or backward directions with the same symmetry breaking parameter. So that wouldn't be the reason.
So here, this is the symmetry breaking case, and sorry, this epsilon y is varied in this direction.
Yeah.
And when we are moving in the backward direction, the system from the steady state goes to the oscillatory state for a different value of coupling strength, epsilon y.
Okay, okay, thank you.
Yeah. So I just want to clarify one point. You are saying that in the earlier case, not this case, the previous one, the system first goes to an explosive transition to an oscillatory state and then later to amplitude death.
Yeah.
Am I correct?
Yeah.
So in that oscillatory state then, you are only checking R. Did you check the synchronization error also? Because otherwise it's only phase synchronization.
Yeah, it is only phase.
It's only phase synchronization.
It is right
Okay.
now, it is only phase
Okay.
synchronization. Yeah.
That's one clarification. The other is, it goes to amplitude death because your alpha n is not equal to alpha h.
Alpha n is not equal to alpha
If you
h.
take alpha n equal to alpha h, I don't think you will get amplitude death.
Yeah, there is no amplitude.
There is no amplitude
Yeah,
death. Okay.
yeah.
Thank you.